We're going to continue to work with series, and in particular we're going to be looking at properties of power series. Last section we looked at Taylor series, and now we're looking at power series with the same idea of being able to rewrite things in terms of a series. So before we get started on too much, we better define what a power series is. So when we talk about a power series, it's kind of based on a geometric series. The formal definition is if x is a variable, then an infinite series of the form, and this is kind of the important part here. This should look a little bit familiar to you. K equals 0 to infinity of a sub k times x to the k, and only the x is raised to the k here, then is equal to a naught plus a sub 1 x sub 1 plus a2 x squared plus a3 x cubed. Kind of this pattern continues on indefinitely as k goes toward infinity. Then this is called a power series. Now there's some particular characteristics about a power series. First of all, we always want to know how a power series is centered. And for this particular one, this series is centered at 0, meaning that's where we're trying to make our best estimate, is at 0. So we could look at an example, kind of like we did for the other section. Let's say we have some curve like this. It looks suspiciously like the sine curve. And if we wanted it centered at 0, that's where we're talking about right here, c equals 0. We're trying to do our best job at c equals 0. Now if we could have a different series, we could say I could center it at pi over 2. So not every power series is centered at 0. Some are centered at different values. So let's go ahead and look at what that would look like if we had some power series centered at different values. Let's look at k equals 0 to infinity. And let's look at a sub k times x minus c to the k. This is a power series centered at c. Now we know it's centered at c because of this minus c right here. Now if this would have been x plus c, it would have been centered at negative c. So it's always the opposite there, kind of like when we're working with some parabolas and things like that back from college algebra. We could also look at a k equals 0 to infinity x to the k. This is a power series centered at 0. And we know it's centered at 0 because I'm not subtracting anything from this base. It's not x minus 2 or x minus 7 to the k, it's just x to the k. Let's look at another one for an example. Let's look at k equals 0 to infinity again, and let's look at x plus 1 to the k. This is a power series centered at negative 1. Why negative 1? Because it's x minus a negative 1 to fit this form of x minus c. Now this looks suspiciously to me like a geometric series. Remember, a geometric series was a times r to the n, or a times r to the k, and that looks just like this. Now the implied a is 1 for both of these last two that we looked at. So power series are what we're talking about. They kind of look like a geometric series to me. Let's see if we can use some of those characteristics to keep building on this idea. So a few important characteristics. A power series can be viewed as a function. So it passes the vertical line test. It's a function where the domain is the set of all values of x where for which the power series converges, because we want it to converge. And when it converges, it means that we're doing a good job of estimating where the function is. So up here in this particular case, I'd want it to converge. I'd want it to do a really good value right here at its center. Also, another characteristic that will be interesting to know about, every power series converges at its center. So every single power series that we work with will converge at its center. And this totally makes sense, because if we look at this little graph up here, I can draw a line that's going to touch at this center, and it's going to guarantee convergence there. And again, that center is C. Therefore, what we can say here then is the center C is in the domain of my function f that I'm trying to work with. So let's see what this looks like graphically. We could have some sort of a curve. We'll have three cases here. So we could have case 1. We'll call this case 2 and case 3. So case 1. So at case 1, let's say we have some sort of a graph, and we can use the same graph for each one of these. So case 2 and case 3 will use the same graph. For case 1, let's go ahead and mark our center right here at C. If I draw my best estimate, I can converge at its center right there just by drawing some horizontal line. So this is a case where it only converges at the center C. Okay, case 2, I could converge on an interval. So let's draw where I could converge on some sort of an interval. So I could do an estimate, and I could do pretty darn good in converging to C. And if you notice, I hit from here to here on my graph, so I do a pretty good job. So this converges on the interval. And C is the center. Now what we don't know is about these endpoints. Well, let's say the left endpoint is B, where it's converging, and the right endpoint is D. So I have to check the endpoints, because I don't know about endpoint convergence. And we'll show you how to do that. So I could have a situation where it converges, and I have brackets for B and D where C is the center. That means it converges at both left and right endpoints. I could have left endpoint converging, right endpoint diverging. I could also have left endpoint converging, right endpoint diverging, and I could have both endpoints diverging. So I have to check to see which situation that we have here. Third case is it converges for all x, including the center. So let's call this our center again. And let's say I can come up with a really good series approximation that basically traces that graph. So this would be a case where it converges for all x. And of course that would include the center. I don't have to check the endpoints here, because for all x would be negative to positive infinity, and we never bracket infinity. And a couple of things to keep in mind once we start talking about these intervals of convergence and point convergence is the domain of a power series centered at C has only one of the following characteristics. Of only one of the following can be true. So this is going to be important. We're going to use this quite a bit. So case 1. So for case 1, the series converges only at C, and that's the picture that we drew up above. And if that's the case, then I have what is called a point convergence. And that's at x equals c. The radius of convergence, meaning how far can I move off of the center and still converge, is going to be equal to 0. So radius of convergence, ROC, and a lot of times we just call it R for radius of convergence, is 0. I can't move off the center at all. Now, I don't have to talk about an interval of convergence here because that's not possible because there is no interval. Let's look at case 2 from up above. For case 2, the series converges absolutely. For the absolute value of x minus c less than some value of r. And r is this same radius of convergence. Now the absolute value is here, and remember, I can rewrite this interval, and if I rewrite the interval I'd have to check the endpoints. But let's write out a few other things. And it diverges for the absolute value of x minus c greater than r. Now for convergence, what we can do is we can talk about the radius of convergence, which of course is just equal to r. My interval of convergence would be c minus r and c plus r. And then I would have to check endpoints to figure out are these parentheses or brackets. And I can have some parentheses and some brackets. They don't have to match on either side. This is called my interval of convergence, and it's often abbreviated IOC. So interval of convergence, different than the radius of convergence. So we're learning quite a bit about these geometric series, or these power series, and we haven't really worked any problems yet, but there's a couple things we still need to know before we can. So to get started with case 3, we need to remember that the domain are all real values of x, or all x values. So let's look at case 3. Case 3, the series converges absolutely for all x. So that tells me the radius of convergence then equals infinity. So that's r equal infinity. The interval of convergence is what we just wrote up above, is negative to positive infinity. And I don't have to check endpoints here because I can never bracket infinity. They're always going to be parentheses for this case. Now remember, ROC equals r, which is the radius of convergence. This means how far can I move off of the center and still match that graph or still converge. IOC, it's a C up there, is the interval of convergence. And with the interval of convergence, basically this is going to be the set of all x values for which the power series converges. Okay, now how do we figure all this out? What test do we use? Well, as it turns out, to determine, and this is kind of a big important thing here, determine the interval of convergence, use the ratio or root test. So this is from the last unit So I hope you remember the ratio and root test because we're going to be using them a lot here. Okay, let's go ahead and look at those real quick. Okay, so this is a screenshot from your formula sheet for the ratio and the root test. So just let's do a quick review. So for the root test, I use things that have a power of k in them usually. So for the root test, I take the limit as n or k approaches infinity, the absolute value of the kth root of the absolute value of a sub k. If that is less than 1, then it converges. So this is how I would force convergence. If it's greater than 1, such as infinity, that would fall in this particular case, it diverges, and I have point convergence. And then, of course, it's inconclusive if I get the limit exactly equal to 1. And that's going to be the same for the ratio test as well. But for the ratio test, I do the absolute value of the next term divided by the current term. So again, this would include infinity. And of course, I have inconclusive at 1. Now, usually we call this limit rho for the root test and r for the ratio test, but I think those are pretty interchangeable. So we're going to be using these a lot. We're also going to be using a lot of the other tests that we learned, because we'll have to be checking the endpoints, and a lot of times they're a p-series, a geometric series, or the alternating series test would work for those. So having looked at that, let's go ahead and get started with some questions. The first problem that we're going to look at here is we're not given a power series. They just already give us the interval to work with, so we're lucky here for that one. So they're already telling us that this is where it's converging, and here's where it's diverging. So converging less than or equal to 102, greater than 102 for diverging. It says determine the radius and interval of convergence. So I don't care about the diverge, I only care about the converge. So to calculate that, what I would do is I'd start with this interval of convergence, and I have 6x minus 12 less than or equal to 102. This is basically ready to go because I already have the equal sign. So I don't really have to check my endpoints because they're already provided to me here. Otherwise, I actually would check those endpoints, but here they give them to us in this case. And I could rewrite this as negative 102 less than or equal to 6x minus 12 less than or equal to 102. That's the definition of the absolute value. Let's say I have the absolute value of x less than a or less than or equal to a, doesn't matter. That's negative a less than x less than a. It means between is what that ends up looking like. I would add 12 to the left, the middle, and the right. So if I add 12 to the right, I'd end up with 114. If I add 12 to the middle, I end up with 6x. And if I add 12 here, I'd end up with a negative 90. Then I divide through by 6. So if I divide through by 6 here, I get 115. So I get negative 15 less than or equal to x, less than or equal to, let's do 119 here. So this is my interval of convergence. Now the radius of convergence I already passed by a little bit ago. I can find the radius of convergence easily from the interval of convergence that I have here. So let's go ahead and check what that would look like. The radius of convergence r, let's mark this first so we don't lose that. The radius of convergence would be 19 minus a negative 15, so the right minus left over 2. So this is the same as 19 plus 15. So this is going to be 34 over 2, which is 17. So r equals 17. So those are the two values. Now, is there a spot that I could have got this sooner? Because in my math lab, they always ask for the radius of convergence first. Well, in order to answer that, we'd have to look up above here. So let's go way up here. And we do have to look at the interval of convergence right here. So this x minus c is less than r. That's kind of our important thing here. But I don't have an x minus c less than r. I have a 6x minus 12 less than r. So in order to figure that out, I'd have to be trying to find this right here. Now it could be less than or equal to or less than, it doesn't matter. They gave us the equal to, so I know it's point convergent on the endpoints. So what I'd like you to think about here is I can always find the radius of convergence from the interval, so I don't have to do the step that I'm about to do. So if we take this 6x minus 12 less than or equal to 102, I could factor a 6 out of here. And the absolute value of 6 is 6. So I could divide both sides through by 6, and I have the absolute value of x minus 2 is less than or equal to 17. So there's my radius of convergence, 17. It matches right here. Now what's my center? This tells me my center is 2. So C equals 2. I can also find my center here if I look at these in terms of finding the midpoint between 2 points. I could look at the midpoint of negative 15 to 19. So I'd have 19 minus 15 all over 2. So that would be 4 over 2, which equals 2. So that's my center. Now, interval of convergence, I can use my set builder notation. That means with the less than greater than signs, or I could also use my bracket notation like we did below. And I think bracket notation is what is preferred in my math lab for this assignment. Now our next problem that we're going to be looking at, they're not giving us that radius of convergence or that possible interval of convergence to begin with. We're going to have to be able to come up with that. So we're going to have to use either the ratio test or the root test. And right away on this one I see that we have a power of k, so I'm going to have to use the root test. Now also, along with that, they want us to find the radius of convergence and then to test the endpoints. Okay, so we're guaranteed a radius of convergence, and I'm guessing it's not going to be negative to positive infinity, because if it was, I wouldn't have to test the endpoints, and they're saying test the endpoints. And I'm also not thinking this is point convergent either, like at just the center, otherwise they wouldn't say test the endpoints. So let's go ahead and get started looking at this. We have to use the root test, so as usual I always name the test. And then I look at the criteria for the test. So if you want to look on your formula sheet to see the criteria for the test, you can. So remember, I'm always looking at that row, the limit as k approaches infinity of the kth root of the absolute value of 19x to the k. Now the 19 and the x are raised to the k, then that's important to note that difference. I can put this in parentheses, I can put the k inside the absolute value and rewrite that if I want to, or you can just go ahead and pull that out. So this would be the kth root of the absolute value of 19x to the k. Now the k's cancel each other out, so I'm left with a limit as k approaches infinity of the absolute value of 19x. Because again, this is going to be the kth root over the kth power, and they cancel. Well, k is our variable here. 19x is our constant. So this is just equal to the absolute value of 19x. Now what I want to do is I want to force convergence on this. So I want to force convergence, and I'm going to say this is less than 1. Now where does that come from? Remember, look on your formula sheet. If I want to force convergence right here, I have to make that less than 1. So that's where this is coming from. So force convergence. So I force this to converge by making it less than 1. And so now I'm looking at this converges on the interval absolute value of 19x less than 1. So now I'm looking for the radius of convergence and the interval of convergence. Well, remember, it converges if the absolute value of x minus c is less than 1. So in order to make this happen, I could pull that 19 out front. It is positive, so I have 19 absolute value of x is less than 1. Divide through by 19, and I get absolute value of x is less than 1/19. So this is my radius of convergence. So r is equal to 1 over 19. Now I could have also done this a different way. I could have started with this absolute value of 19x, and I could have rewritten this using the definition of absolute value here, divided through by 19, and I would get a negative 1/19 less than x less than 1/19, and this gives me my interval of convergence almost. I need to check endpoints. Okay, but I can also find the radius of convergence here. I already found it as 1/19 up above, but this is another way I can find it. So the radius of convergence, I could take my right endpoint minus my left endpoint, so minus a negative over 2. So this would be 2/19 over 2. When you divide by a fraction, you multiply by the reciprocal. So the reciprocal of 2 over 1 is 1/2. And I'm left with 1/19 for r. So that's another way you could find it. Now, back to what we're up to here. I need to check endpoints for my interval of convergence. So right now I'm looking at negative 1/19 less than x less than 1/19. So the endpoints I need to check are x equal negative 1/19 and x equal 1/19. And where do I check them at? Check them in the original. So the original was the sum, whoops, of 19x to the k. And remember, the 19 and the x are raised to the k. So if I plug a negative 1/19 in there, I'm going to have 19 times a negative 1/19 raised to the k. This is going to be negative 1 to the k. And let's see what we have going on over here. I'm using the same original series. If I plug in a 1/19, I have 19 times 1/19 to the k. The 19's cancel and I have a 1 to the k. So on this left one is an alternating series because I have the negative 1 to the k, so it's going to alternate. But it also looks like a geometric series. In fact, both of these do. So I'm going to test these using the geometric series test. And because this is the form a times r to the n, or r to the k, in this particular case, r is equal to a negative 1, and I test the absolute value of r, so the absolute value of negative 1 is equal to 1. Now if you look on your geometric series sheet, on your formula sheet, geometric series diverges for an r greater than or equal to 1. So this is greater than or equal to 1, therefore it diverges. Same thing's going to happen here. This is a geometric series test. I could also use the nth term test for divergence here as well. I like the geometric series test. So this is r equal 1. I look at the absolute value of r as the absolute value of 1, which is greater than or equal to 1, therefore this diverges. So each of the endpoints diverge. So that tells me then I can officially say my interval of convergence is negative 1/19 to 1/19. Because at these endpoints they diverge, I don't have equal signs and I don't have brackets. And remember, my radius of convergence for this was just equal to r, was equal to 1/19 from above. So this kind of summarizes everything for this problem. So I basically did 3 series tests. I did the ratio test, and then I did 2 geometric series tests for each of the endpoints. So having that sheet on your formula sheet with all the different series tests is going to be super handy. So here's another similar problem. We're going to take the same approach as we did for the last one. It says determine the radius of convergence of the following power series, then test the endpoints to determine the interval of convergence. Okay, so let's go ahead and start with, I have a power of k here, so I'll start with the root test. So you should always use the ratio or the root test to start. Remember, anytime you have a power of k, that's your variable that's going from k to infinity, or 1 to infinity, or 0 to infinity. That's the best test, is the root test. If I have factorials, or if I have x to the 4th, that type of thing, then ratio test is better. So I use this value for rho. I look at the limit as k approaches infinity of the kth root of the absolute value of 10kx to the k. Now remember, I can put the k inside the absolute value, or I can pull it out. The effect is the same. The kth root and the kth power cancel each other out, so I'm left with the limit as k approaches infinity of the absolute value of 10x k. Okay, now 10 and x are constants because k is my variable of interest. So this would look like the absolute value of 10x times then the limit as k approaches infinity of the absolute value of k. Well, k is positive because it goes from 0 to infinity, but I can leave my absolute value there. This limit as k goes to infinity is infinity. So I have 10, absolute value 10x times infinity is just equal to infinity. Infinity is greater than 1. I can't force infinity to be less than 1, so I can't force convergence here, so this diverges. Okay, so diverges. So the radius of convergence is equal to r is 0. The interval of convergence is just going to be equal to a single point, is going to be the center, c, in this particular case c equals 0. Why does it equal to 0? Because I have the absolute value here, if I wanted to look at this, or I could look at this in terms of x minus c to the k. I'm not subtracting anything, so I'm subtracting 0, so that would be my center, or my interval of convergence is just the center, that single value. So again, for this next one, we want to find the radius and interval of convergence, and we have this power of k. So I'm going to be using the root test. So name the test. You always need to name the test that you're going to use. You describe the conditions of the test. Rho is equal to the limit as k approaches infinity of the kth root, and I'm getting that from my exponent right here, of the absolute value of x over 5 to the k. Now what's happening here is the k power and the kth root cancel each other, and I'm just left with the limit as k approaches infinity of the absolute value of x over 5. Well, x and 5 are constants here. K is the variable, so I'm just left with the absolute value of x over 5. Now this I can force convergence with. So let's go ahead and force convergence here. And the reason we force convergence is if you look on your formula sheet, the root test will converge for values less than 1. So force convergence. And I should be able to find my interval and my radius of convergence now. Let's start with the radius of convergence. Remember, that's going to look like the absolute value of x minus c is less than 1. So I'd have to get this in that form, and when I do that, I'm going to start with, well, I don't quite have my interval yet, so let's work on this end. So I'd multiply both sides through by 5, and I get the absolute value of x is less than 1. So 1 is my radius of convergence, which is just equal to r. So I get r equal 1 here. Now let's go ahead and rewrite this. I'm sorry, that's not right. That's 5, because I multiplied both sides through by 5. Okay, so now I rewrite this in interval notation, this absolute value of x less than 5. The definition there is -5 less than x less than 5. So that means all the values between -5 and 5 would make that to be a true inequality. But this is not done. I need to check my endpoints. So let's go ahead and check endpoints. X equal -5 and x equal 5. So this will plug back into my original. My original was k equal 1 to infinity of x over 5 to the k. Same over here, k equal 1 to infinity, x over 5 to the k. Let's see here. Okay, let's go ahead and plug in x equal -5. If I do that, my series is going to look like -5 over 5 to the k. -5 over 5 is -1 to the k. This is a geometric series. You could also test this using the nth term test for divergence, alternating series test. Now remember, whenever we use a test, we have to name the test. In this case, r is equal to a -1. In the geometric series test, I always check the absolute value, and this is greater than or equal to 1, so it diverges. So the left endpoint diverges. And let's do the same thing over here. If I plug in a 5, I get 5 over 5 is 1. So I get 1 to the k. This is a geometric series. Remember, a geometric series looks like a times r to the k. A at both of these is a 1. So here r is equal to 1. I look at the absolute value of 1 is 1. This is greater than or equal to 1, so therefore it diverges as well. So both endpoints diverge. I can't have an equal or a bracket there. So r was equal to 5, the radius of convergence, and the interval of convergence was equal to -5 to 5. No brackets, no equal sign, because both of the endpoints diverged. So again, we use the root test. The next problem that we're going to be looking at, they're not giving us the series. We have to come up with it based on the terms of the series. So this is a little bit different. We're going to have to rely on our knowledge that we learned in a previous unit to be able to rewrite this. So first of all, we need to determine the radius and interval of convergence. But in order to do that, I need to figure out what this series even is. So let's go ahead and start thinking about this. When I write out this series, I'm going to start with k equals 0 or 1, I'm not sure. I notice this is alternating, so I'm going to have a -1 to the k or k plus 1. I need to figure that out. And then notice my powers are even in the exponent. So this would be x second 2, 4, 6, 8. So I should just be able to go 2k. Because if I start with k equal 1, and then go to 2, that would be 2, 4, 3 times 2 is 6, etc. So that works out pretty good. And then, if I'm going to start with k equal 1, my first term is positive. So if I go -1 to the k, that's going to start odd. So I'll have to go k plus 1 here. I could also go k minus 1, doesn't matter. Now this denominator, let's figure this out. 3, 4, 5, 6. So this looks like k plus 2 factorial. If I start with 1, 1 plus 2 is 3, and I start here. So there's my series. So I see pretty clearly here that I have a couple things going on. First of all, I do have a 2k power. I don't have the k in the base though, and I also have a factorial. So because of the factorial, I'm going to go ahead and use the ratio test. Now the ratio test, I look at r is the limit as k approaches infinity of the absolute value of the next term. Now I don't need to include the -1 to the k plus 1 here, because when I take the absolute value, I just look at the absolute value of all the terms, positive or negative. So this would be, the next term would be x to the 2 times the quantity k plus 1. It's not 2k plus 1, it's 2 times the quantity k plus 1, all over k plus 1 plus 2 factorial. So that's the next term divided by my current term. And again, I can ignore the -1 to the power. This would be x to the 2k all over k plus 2 factorial, absolute value. So key here is when you divide by a fraction, you multiply by the reciprocal. So I'm left with the limit as k approaches infinity of the absolute value. So let's think about what this is. This is going to be x to the 2k times x to the 2, because this ends up being 2k plus 2. And when you multiply like bases, you add exponents. So x to the 2k plus 2 came from x to the 2k times x to the 2. And this is going to be over k plus 3 quantity factorial times the reciprocal of k plus 2 factorial all over x to the 2k. So this is what we're simplifying. Well, really clearly right away I can see x to the 2k cancels. Now k plus 3 factorial is k plus 3 times k plus 2 factorial. So these cancel. And it looks like to me I am left with the limit as k approaches infinity of the absolute value of x squared all over k plus 3 factorial. Well, if we want to pull out constants here, I could pull out the absolute value of x squared, and I'd be left with the limit as k approaches infinity of the absolute value of 1 over k plus 3 factorial. Well, this term, this piece right here, is going to 0 because the numerator is fixed, the denominator is increasing without bound. 0 times x squared is equal to 0. And if we go back and look at our test sheet of all the different series tests, for the ratio test, 0 is less than 1. So therefore this converges absolutely for all x. Now, I didn't have to force convergence here. 0 is less than 1. I can't, no matter what I do with x, this is going to be less than 1. So that's why it converges absolutely for all x. And the x's come from right here. So no matter what x values I plug in here, this is going to converge. So the interval of convergence and the radius of convergence here, r is equal to infinity, because it converges for all values. And my interval of convergence, because it converges for all values, is negative to positive infinity. So this one converges absolutely for all x, because I can't change this to converging for some x, because it will always converge, because I have x times 0 is always going to be 0, which is less than 1. We're also going to find the radius of convergence. And while we're working on this, we'll also find the interval of convergence as well. So one comes from the other, but the radius of convergence is what we're going to focus on here. Now I see some powers here and I see some factorials, and because of the factorials I'm going to start with the ratio test here. So the ratio test, I'm looking for this ratio r equals the limit as k approaches infinity of the absolute value of the next term. So that would be k plus 1 factorial, x to the 3 quantity k plus 1, all over 5 times the quantity k plus 1 factorial. Now notice I just don't go 5k plus 1. That's not equal to 5 times the quantity k plus 1. These are very different things. Okay, so that's the next term, and then we're going to divide it by our current term. So that would be k factorial, x to the 3k, all over 5k quantity to the k. Now remember, when you divide by a fraction, you're multiplying by the reciprocal. So we have a lot of simplification to do here. So I have k plus 1 factorial. This would be x to the 3k times x cubed, because this is 3k plus 3. And when you multiply like bases, you add exponents. So x to the 3k plus 3 came from x to the 3k times x to the third. And then this is going to be 5k plus 5 factorial. And when you divide by a fraction, you multiply by the reciprocal. So this would be 5k to the k. And remember, it's the 5 and the k to the k, over k factorial x to the 3k. Now remember, this is all absolute value. Now our hope is some things cancel here, and we do see some things canceling. So x to the 3k's cancel. I have a k factorial here. I feel like I dropped a factorial somewhere. Let me look at this. $5k. Yep, it's right here. This denominator was a k. It was not a factorial. So this should be to the k here. So make sure when you're writing this out, you fix that up. It should be to the k. And then that flips. Yep, that makes more sense. So then this k factorial will cancel up here, leaving me with just a k plus 1. Because remember, k plus 1 factorial is k plus 1 times k factorial. And there's some more simplification we can do here, but let's rewrite this first and see what we're left with before we simplify further. So we have the limit as k approaches infinity of the absolute value. Okay, so I'm left with k plus 1, x cubed, And then this 5 to the k, that's the same 5 to the k times k to the k. So this can be rewritten as 5 to the k times k to the k. And then this piece right here can be written as 5 times the quantity k plus 1 to the k, which was over here. So I can rewrite that as 5 to the k times k plus 1 to the k. So 5 to the k times k plus 1 to the k. So again, my hope is some things cancel here. And I think we also have a k plus 1 here in the denominator. So this k should have been k plus 1, because remember this was the next term, so this would have been a k plus 1, plus 1, k plus 1. So this would be 5 to the k times 5 to the first, and then this would have been an extra k plus 1 here as well. So the way that came in is when I rewrote this, remember I had a factorial here, I think, and then I remembered that this was a k that was given, but this was the next term divided by the current term. So that's where the error was. So let's make sure that that's correctly followed through. Okay, so that looks correct now. So the 5 to the k's cancel, and what else cancels? The k plus 1's. So then I can pull out an absolute value of x cubed over 5, because those are my constants. And then I'm left with the limit as k approaches infinity of the absolute value of k over k plus 1 to the k. So that's what's left right here for my limit. Well, this is a variable to a variable, so this is a little bit of work here we're going to have to do. Because I have a variable to a variable, I need to kind of think back. I need to use the limit of the logs here. So I'm going to keep this in mind, and I'm just going to call my limit equal to y, and I'm just going to look at the limit as k approaches infinity of the absolute value of k over k plus 1 to the k. Now k is going from 1 to infinity, I think, on this one. I don't really remember, but they're all positive values, so I could drop the absolute value. Again, this is going to go back in at the end of the problem, so we don't want to lose that. So what I'm going to do is I'm going to take the natural log of both sides. And when I take the natural log of both sides, the overall effect here is the log of the limits is equal to the limit of the logs. And the reason I do this is so I can switch these around, and I can put the limit on the outside, and then I can pull this k out front, k over k plus 1. So now I'm ready to take this limit to see what happens. Well, this term will go to infinity, and this will go to the natural log of 1, because the degree in the numerator and the degree in the denominator are the same. So 1 over 1 is 1. Natural log of 1 is 0. So this is infinity times 0, which is indeterminate. Now it's not indeterminate L'Hopital's, it's indeterminate do more work, which is rewrite it. So what I have here then is the natural log of y equals the limit as k approaches infinity of k times, how am I going to rewrite this? Natural log of k over k plus 1. Instead of k out front, let's rewrite that as 1 over k. So I'm left with the natural log of y equals the limit as k approaches infinity. So now I'm going to end up with natural log of 1 is 0. So I get 0 over 0, which is indeterminate L'Hopital's. So now I can actually work this problem. So I have natural log of y equals the limit as k approaches infinity. So the degree in the numerator and the degree in the denominator I don't have yet. I have to use L'Hopital's. So L'Hopital's is the derivative of the bottom, so that's negative 1 over k squared. The derivative of 1 over k is negative 1 over k squared. And the derivative of the top would be the natural log of u is 1 over u, so this would flip, times the derivative of u. So the derivative of u, I would use k plus 1 as the bottom, times the derivative of the top minus the top times the derivative of the bottom, all over the bottom squared. Well, I'm not ready to take this limit yet. I need to do some rewriting. So I'm left with k plus 1 over k and then the top I'm left with k plus 1 minus k all over k plus 1 quantity squared. And of course this is negative 1 over k squared still, so we're still rewriting. The natural log of y is equal to the limit as k approaches infinity. So let's see what we have here. The k plus 1's cancel, and I'm just left with the k plus 1 here. Here I'm left with k plus 1 minus k is just 1. So it looks like to me I'm left with 1 over k times k plus 1. And then when you divide by a fraction, you multiply by the reciprocal. So negative 1 over k squared becomes negative k squared over 1. And we're going to have to simplify this a little bit more. The k's cancel, and I'm left with a negative k on top. And I'm left with the natural log of y is equal to the limit as k approaches infinity of negative k over k plus 1. So we're using logarithms here to help us take this limit. Well, we're still not done. It seems like we should be, but we're not done yet. So now I'm left with the natural log of y on the left still is equal to the limit as k approaches infinity. Now up here, if I would have taken that limit, I would have had negative infinity over infinity, which is an indeterminate L'Hopital's. So now I can apply L'Hopital's rule. The derivative of negative k is negative 1. The derivative of k plus 1 is 1. So I'm left with the natural log of y equals the limit as k approaches infinity of negative 1 is negative 1. Now I need to remember this up here, this x cubed over 5 up here at this point. As soon as I can figure out what y equals, I need to pop that up front, but I want to make sure you remember that it's there. Now remember, natural log of y is log base e of y. So I get log base e of y equals negative 1. And then I rewrite that in exponential form, and I get e to the negative 1 equals y, or y equal 1 over e. Okay, so now remember, up top I have this absolute value x cubed over 5. So let's pull that back in. So the absolute value of x cubed over 5 times 1 over e, and I want to force this to converge. So I'm going to make it less than 1, so I'm going to force convergence here. This can't go to infinity on this one because there's no infinities involved anywhere. Okay, so let's think about what we have here. I want to clear the fraction, so I multiply both sides through by 5e, so I get the absolute value of x cubed is less than 5e. And then what I want to do next is I want to look at my power here, and so I'm going to take the third root of both sides. So I get the third root of x cubed is x, and then I have the third root of 5e here. This is my radius of convergence. So my radius of convergence is equal to r. It's the cubic root of 5e. So that's how far I can move off the center and still say that this converges. So natural logs are important here, and I know I'm going to have to use natural logs whenever I see a variable to a variable. Okay, our next one that we're working with is a little bit different. What they give us here is they give us the power series that will work as best defined for the function 1 over 1 minus x. Okay, so instead of us trying to find that series, they give us the series. So we have the geometric series f of x equals 1 over 1 minus x, and then I have that this is approximated by the geometric series k equals 0 to infinity x to the k for the absolute value of x less than 1. And remember, this means negative 1 less than x less than 1. Now let's remember also from a geometric series, and this is on your formula sheet, you can look this up. If the geometric series converges, and remember the geometric series will converge if we have the absolute value of r less than 1, then it converges to the sum s equal a over 1 minus r. Okay, so keep that in mind, because this kind of looks like a over 1 minus r a little bit. Okay, so it says find the power series representation for the following function centered at 0. Give the interval of convergence of the new series. Well, these look almost identical. The only difference is we have a 2 here. So I'm replacing the x with 2x. So I'm going to replace this x with 2x. So this is going to look like k equals 0 to infinity of 2x to the k. That's what I have here. Now, what ends up happening here is I have this new series now, and with this new series, I need to find the interval of convergence for this series I just wrote. So this definitely looks like a power of k, so I'm going to use the root test here. So we always name our test. We show the criteria for the test. Rho equals the limit as k approaches infinity of the kth root of the absolute value of 2x in this case to the k. So both the 2 and the x are raised to the k. So this is equal to the limit as k approaches infinity. The kth root and kth power cancel, and I'm left with the absolute value of 2x. That's a constant, so the limit of a constant is a constant. Now the reason it's a constant is our variable is equal to k. I want to force this to converge, so I set this less than 1, and that's from your formula sheet as well. How do you force a root test to converge? You make sure that this limit is less than 1. So we were charged with finding the interval of convergence here. So I could rewrite this right away. So let's keep working on this, the absolute value of 2x less than 1. I could rewrite this as -1 less than 2x less than 1, or I could have divided through by 2 and then rewritten it, doesn't matter. Divide through by 2 and I have -1/2 is less than x is less than 1/2. So this is my interval of convergence, but I have to check the endpoints before I can say it's my official interval of convergence. So let's go ahead and check x equal -1/2, and let's go ahead and check x equal 1/2. And this goes back into my original, and here's my original right up here. So this is k equals 0 to infinity of 2x, but 2x is 2 times -1/2 quantity to the k. In rewriting that, I get k equals 0 to infinity, so I get -1 to the k. And let's see what we get over here. I get k equals 0 to infinity, 2 times 1/2 quantity to the k. So this ends up being 1 to the k. Now, the left one is an alternating series, so I could use the alternating series test on this, but both of these are geometric series. So there's more than one test that's a possibility here. The geometric series looks like a times r to the k. So both of these are geometric series. So in this geometric series, and always name the test, r is equal to a -1. I take the absolute value of r, which is the absolute value of -1, which is 1. And for a geometric series, that's greater than or equal to 1, so therefore it diverges. Let's do the same thing here. R is equal to 1. The absolute value of r is what I'm interested in testing. The absolute value of 1 equals 1, which is greater than or equal to 1, so therefore this diverges. So I don't have equality at either endpoint, so my interval of convergence here is -1/2 to 1/2. Diverges, so I have no brackets, I only have parentheses. Now the center here is 0. That's kind of interesting because I can just look at the midpoint between -1/2 and 1/2, and the radius of convergence is 1/2. But it didn't ask me for that in this particular problem. Okay, I know the lecture is getting a little bit long, but I want to make sure I run through at least 3 more problems, so that way when you get to the homework set, you have seen most of the types of problems that you're going to be seeing in your homework. Okay, so next one. It says use the power series. So they give us a power series here, and they give us the series that it's equivalent to, and it gives us values of x between -1 and 1. Notice, this is kind of interesting here for me, I have an equal sign, I have less than or equal to here, and then I have just a less than here. So we have to keep that in mind. It's a little different than the problem we just did. To find the power series representation for the following functions centered at 0, give the interval of convergence. Okay, so let's see how this is changing. Well, the natural log of 1 minus x is this piece right here. And out front, I just have to have a 3x squared. So that's what I'm going to do. I'm going to rewrite this then, this new series, as k equal 1 to infinity. And there's a negative sign out front. And then what I'm going to do is I'm going to have a 3x squared here times x to the k all over k. Now I want to rewrite this a little bit. I don't want to leave it like this. So I can pull the 3 out front because that 3 out front is just a constant. So I'm going to pull that 3 out front with a negative. K equal 1 to infinity. And then it looks like I'm left with x squared times x to the k. That would be x to the 2 plus k, because when you raise power to a power, you multiply the powers, but when you multiply like bases, you add exponents and then have a k. So that would be my rewrite here. Now this is the series that I want to check. So I have to decide, how do I want to check it? Well, it looks like to me I do have a power in the exponent of a k, so I think we'll use the root test here. Now if we use the root test, what's going to happen to this k down here? Because there's no power of k on there. So even though I have a variable in the exponent of a k here, we would have to have that k here as well for the root test. So instead of using the root test, let's go ahead and try the ratio test. You can run through the root test if you want and see if you could get the same results or similar results, but I think the ratio test will work a little bit better here. So we're looking at r equals the limit as k approaches infinity of the absolute value of the next term. So this would be -3x to the 2 plus k plus 1. That's the next term. K plus 1 in the denominator, divided by our current term. But when you divide by a fraction, you multiply by the reciprocal. So the k would pop up top, and then the denominator would have -3x to the 2 plus k. So I am dividing by the current term, but when you divide by a fraction, you multiply by the reciprocal. So I have a lot of simplification I can do here. The limit as k approaches infinity. Now because I'm looking at the absolute value, the -3's of course become 3, but they cancel anyway. And then I'm left with, let's see here, x to the 2k plus 1. That would be x cubed x to the k times k. So this is x cubed plus x to the 3rd plus k. So I can rewrite that, and here's my k. In the denominator here, I'm going to have k plus 1 times x squared x to the k. So let's look to see what cancels here. Looks like the x to the k's cancel. X cubed cancels with the x squared, leaving me with an x. And it looks like to me I have the limit as k approaches infinity of the absolute value of x times k all over k plus 1. I can pull the absolute value of x out front because it's a constant, and then I'm left with the limit as k approaches infinity of k over k plus 1. You could leave the absolute value there or not. All values of k are positive. Well, here this is going to be equal to 1 because the degree in the numerator equals the degree in the denominator, and then I'm going to make this less than 1 because I want to force convergence. Okay, and if you notice here, they're giving us similar information. So my interval of convergence based on this is going to be -1 less than x less than 1. That's how I rewrite this. Now I need to check in points, so I'm going to check x equal -1, I'm also going to check x equal 1 back into the original function, and this is the original right here that I just wrote. So that's going to be negative 3 sum negative 1 to the k plus 2 or 2 plus k, it doesn't matter, all over k. And this is going to be negative 3. I'm going to plug in a positive 1, not a negative 1 here, my right endpoint. So I have 1 to the k plus 2 all over k. Okay, so let's see what's going on here. So for this left one, I have the negative 3 out front. Negative 1 to the k plus 2 is creating an alternating series here. And for this particular alternating series, remember my indice is going from k equal 1 to infinity. So I don't think I can rewrite this as a geometric series, a times r to the n. So let's keep working on this x equal negative 1. I think we can simplify it a little bit. It's definitely an alternating series. Have the negative 3 out front. And then I have my sum. Now this negative 1 to the k plus 2 can be written as negative 1 to the k times negative 1 squared all over k. Well, negative 1 squared is just 1. So again, I have this negative 3 out front, and I have negative 1 to the k all over k. This is an alternating series test, not a geometric series. This is an alternating series test. So look on your formula sheet. There's two criteria that have to be true for the alternating series test. First of all, when I'm looking at 1 over k, the next term has to always be less than or equal to my current term. And that's true because here the numerator's fixed, the denominator's increasing without bound, which makes a lesser fraction as we move. The next thing has to be true is that when I take the limit as k approaches infinity of the non-alternating portion of the series, which would be 1 over k in this case, I get 0. So check, both of these check. Therefore it converges at x equal negative 1. Okay, now let's come up here to x equal 1. So for x equal 1, I have a negative 3 out front. And this 1 to the k plus 2, 1 to anything is 1. So this is just 1 over k. Well, negative 3, I'm just kind of dragging this along. This is a p series with p equal to 1. So this is a divergent harmonic p series. So if you look at your p series, when I have p less than or equal to 1, it diverges. So it diverges at x equal 1. So my interval of convergence then is negative 1 bracketed because I have convergence, 1 parenthesis because I have divergence on the right. So here I needed to check those endpoints, and notice if we go clear back up to the top, that matches the less than or equal to on the left and the less than on the right, bracket and parenthesis. Okay, 2 more. So for this next one, let's see, they're giving us f of x equals 1 over 1 plus x to the 6. This looks very close to that a over 1 minus r that we were talking about. It says find a power series representation centered at 0 for the following function using known power series. Give the interval of convergence for the resulting series. So this is what I want to think about. Geometric series would look like a times r to the k or a times r to the n. And if this converges, it would converge to s equal a over 1 minus r. So this looks very, very similar. If I could rewrite this as 1 over 1 minus a negative x to the 6th. Well, in this particular case then, a is equal to 1 and r is equal to negative x to the 6th. So I could rewrite this then as the geometric series k equals 0 to infinity of a, which is 1, times r, which is negative x to the 6th, to the k or the n, however you want to write that. And that would be my series. So I get k equals 0 to infinity of negative x quantity to the 6th. The 1, of course, doesn't end up having an effect here. So that's kind of what I'm looking at. Let's go ahead and look at this in terms of either the ratio test or the root test. Now this one's going to be a little bit tricky. It's kind of interesting one. But this looks like a geometric series. So I don't even think we need to use the ratio of the root test. Let's just go after the geometric series here. Actually, I see here that I forgot the k, so let's put that in first. Okay. So as we look at this, when you raise a power to a power, you could multiply the powers. So let's go k equals 0 to infinity of negative x to the 6k. Okay, so let's look at the ratio test. I think we could go after the geometric series a little bit on this too, but we're using consistently the ratio on the root test, so let's stick with that. Limit as k approaches infinity of the next term, so this would be negative x to the 6 times the quantity k plus 1. Remember, it's not 6k plus 1, it's 6 times the quantity k plus 1 all over the current term, which is negative x to the 6k. And then we want to simplify. Limit as k approaches infinity of the absolute value. This would be 6k plus 6, so this would be a negative x to the 6k times negative x to the 6, this is a 6 right here, all over negative x to the 6k. So we have some things that will cancel here, and I'm left with the limit as k approaches infinity of the absolute value of negative x to the 6th. Well, that's a constant, so I could pull that out front, and then I could force some convergence on this. So because I'm looking at the absolute value, I'm going to keep that absolute value out front. So this would be absolute value of x to the 6th, and then I want to force convergence. That's why I make it less than 1. So using our definitions here, we could have negative 1 less than x to the 6th less than 1. And I'm going to split this out into two pieces right now because I can't take that 6th root of a negative 1 because it's an even root, but I can rewrite this as negative 1 less than x to the 6th. Okay, and x to the 6th is less than 1. Now let's rewrite this. X to the 6th is greater than a negative 1. That's just flipping that around so the variable is on the left. And then of course over here I have x to the 6th less than 1. So x to the 6th is always greater than negative 1 for all values of x. So this is negative to positive infinity. So this is true for all values of x. And then over here I have x to the 6th is less than 1. So if I take the 6th root of both sides, I would get the plus or minus 1 is how we could look at this one. So this would equal the 6th root of both sides, so I'd end up with plus or minus 1 is what I want to look at. So let's put these on a number line. So this is going from negative infinity, negative 1, 1, and then to infinity. So what I want to do is I want to check values on these intervals to figure out what's going on, to see what's going to create a true statement here. So on the left part here, I could do f prime, or sorry, I'm thinking slope charts here. We would do f of negative 2, f of 0, and f of 2. So if I plug a negative 2 back into my original, negative 2 to the 6th is not less than 1, it's greater than 1, so this is false. If I plug a 0 in here, 0 to the 6th is less than 1, this is true. And if I plug a 2 in here, 2 to the 6, 2, 4, 8, 16, 32, 64 is not less than 1, so this is false. So this is where my solution lies, is from negative 1 to 1. So my interval of convergence is negative 1 to 1. Now, of course, guess what we need to do next? We need to check endpoints. So let's go ahead and check x equal negative 1 and x equal 1. So if I check x equal negative 1, I'm plugging that back into my original function. That's k equals 0 to infinity minus a negative 1 to the 6k, k equals 0 to infinity. Minus a negative is the same as a positive, 1. So I get 1 to the 6k, which is 1 to the 6 to the k, which is just 1 to the k, which looks like a geometric series to me. And here I get k equals 0 to infinity, and I have minus a positive 1 to the 6k, and I get negative 1 to the 6th, and negative 1 to the 6th is going to be even, so I get 1 to the k here as well. Well, both of these are geometric series. Here r is equal to 1 on both of these. The absolute value of r is what I'm interested in. The absolute value of 1 is 1. So for a geometric series, this is greater than or equal to 1, so therefore these diverge. So my endpoints diverge, and my interval of convergence is negative 1 to 1. I don't have brackets on either endpoint here. I diverge at both of the endpoints. So that would be my solution there. Got a little bit long. Okay, last one. So find a power series representation centered at 0 for the function using a known power series. And we can come up with our own here and give the interval of convergence. So again, this geometric series looks like a times r to the k, and if it converges to s equal a over 1 minus r. Well, this kind of looks pretty close to that. So if we consider this as 14 all over 14 plus x, if I divide through by 14, I get 14 over 14, 14 over 14 minus a negative x over 14. Now why the minus a negative? Because that's the same as a positive. I need to have a 1 here. That's why I'm dividing through by 14. So what I get here is 14 over 1 minus a negative x over 14. So a is 1 in the numerator, r is negative x over 14. So if we write this geometric series, this is going to go from k equals 0 to infinity, and I'm going to have a, which is 1, times r, which is negative x over 14 to the k. The 1 doesn't end up mattering because 1 multiplied by anything is just itself back. So I end up with k equals 0 to infinity of negative x over 14 to the k. So that would be the series that I have here. Now next I want to find the interval of convergence. So I'm going to have to use some sort of a test here. And on this one, remember the last problem I said, oh, we could maybe use a geometric series. I think I'm going to try that one on this one. So let's use a geometric series test to find my interval of convergence. Because I know that if this converges, what it converges to. So geometric series, r is equal to negative x over 14 here. I want to look at the absolute value of negative x over 14, and I want to force convergence. So for a geometric series, that's less than 1. So force convergence. So this is the absolute value of negative x over 14. So I can get rid of the negative sign and leave it in the absolute value. Multiply both sides through by 14, and I get the absolute value of x as less than 14. And then rewriting, I get negative 14 less than x less than 14. And this is my interval of convergence here. Now, I don't need to check the endpoints in this case. You could go through and do that if you want. But for x equal 1, this would diverge. Not for x equal 1, I should be careful here. For r equal 1, this would diverge. So if I had put a less than or equal to 1 here, it wouldn't force convergence. It would converge slash diverge. So I know that these are going to be both less than signs. So this one works pretty slick. The geometric series worked really nice here. So long lecture, but hopefully lots of great information that will help you do your homework. If you have any questions, please let me know. And as usual, I'm always happy to help, and good luck with this assignment. I hope that you enjoy some of